Imagine looking at a simple bouncing ball physics question, thinking you've got it completely in the bag, but you've actually just walked straight into a trap. Today, we are tearing into Cambridge AS and A-level physics, syllabus 9702, and we are going after the big ones: momentum, Newton's laws, and W equals mg. These are the core concepts that examiners use to mercilessly test your fundamental understanding in almost every single exam series. So if you're ready to secure those grade boundaries and stop leaking marks on questions you literally already know the physics for, let's bypass the fluff and get right to work.
60 seconds. That is exactly how long you have to rescue a failing momentum answer before the mock exam timer runs out. You know, it's wild, but there is one specific detail that trips up nearly 60% of candidates when they're calculating momentum in high-pressure exam situations. Students will memorize the formulas perfectly, absolutely flawlessly, yet they still lose the majority of their marks on a single tiny calculation. But here's the good news. We are going to fix that high-frequency misconception today. Rescuing a failing answer is entirely possible once you understand exactly how the examiner actually grades your physics.
So, are you falling into the examiner's three-move chess trap? Let me tell you, this isn't some complex psychological trick. It is simply forgetting the fundamental rule that momentum equals mass times velocity, and crucially, absolutely crucially, velocity is a vector quantity. Examiners intentionally set this trap by presenting a bouncing ball or a rebounding trolley. If you just multiply the numbers together and miss the negative sign that indicates a change in direction, checkmate. You've fallen into the trap before you've even finished writing the first line of your calculation.
Section 1. The examiner's hidden trap. Let's look at the actual top 3 warnings straight from the principal examiner's reports, and let's apply real physics to them so you can see why ordinary revision just fails. First up, using the wrong approach for the context. This usually means assuming kinetic energy is conserved in an inelastic collision. Newsflash, it's not. Second, forgetting format and presentation. In physics, this means omitting the negative signs for vectors moving in opposite directions. And third, providing generic answers. This happens when candidates give vague textbook definitions of Newton's laws instead of stating precisely how force relates to the rate of change of momentum in that specific scenario.
There is this massive, painful disconnect between what you think teachers want and what examiners actually reward. It's superficial breadth versus analytical depth. Superficial breadth is just scribbling down P equals mv and blindly plugging in whatever values are in the question. But analytical depth, that's what gets you the A-star. That means establishing a clear positive direction right off the bat, carefully applying the correct signs for velocity, showing the step-by-step vector addition, and then clearly stating the final direction of the resultant momentum. It's a totally different ballgame.
Section 2. Mastering Method Marks Strategies. Okay, let's talk about getting those quick wins. You have to define fundamental terminology precisely, as the 9702 syllabus requires. Newton's first law? A body remains at rest or in uniform motion unless acted on by a resultant force. Newton's second law? Resultant force is directly proportional to the rate of change of momentum. And the third law? When two bodies interact, they exert forces on each other that are equal in magnitude and opposite in direction. You can't just kind of get the gist of these, you must state them accurately to unlock the method marks.
Now, in just a moment, I am going to show you the one specific examiner clue that changes your answer completely. Honestly, missing this is a guaranteed way to drop a whole grade band, but spotting it makes the whole question straightforward. But first, you need the procedural framework that actually makes that clue obvious. It's all about how W equals mg interacts with Newton's second law. When an object falls, its weight doesn't change, right? But the air resistance opposing it definitely does. Keep that in your back pocket, we'll come back to it.
Section 3. The Deconstruct, Solve, Evaluate framework.
If you want to survive complex momentum problems, you need a system. Step 1. Deconstruct. Extract your masses and initial velocities, but pay strict, paranoid attention to whether an object is moving left or right. Step 2. Solve systematically. Apply the principle of conservation of momentum logically. Literally write out that the sum of initial momentum equals the sum of final momentum. And Step 3. Evaluate. Take a step back. Does the final combined velocity actually make physical sense given the initial masses? If a tiny marble hits a massive boulder and your math says the boulder shoots off at 100 miles an hour, you've messed up.
When you're hit with a question asking you to calculate terminal velocity for a falling object, you need to use this ultimate answer formula. Start with the concept, Newton's second law. Bring in the evidence, weight acts downwards, given by mg, and air resistance acts upwards. Then add your scientific reasoning. As the velocity increases, that air resistance increases until it exactly equals the weight. Finally, finish strong with the examiner wording. At this point, the resultant force is 0, hence acceleration is 0, and terminal velocity is reached. Boom! Top band marks.
Section 4. Interactive Spot the Error Challenge. All right, time to put you in the hot seat. We have a calculation right here for the weight of an object. It says W equals 5 times 9.8 equals 49. I want you to take a second and spot the lethal errors here before the examiner strikes this down. See it? First, look at the missing units halfway through the calculation. And worse, notice the premature rounding of the gravitational field strength. In Cambridge 9702, using 9.8 instead of 9.81 meters per second squared is a fatal flaw. It will cost you accuracy marks immediately.
Section 5. Top band answer correction.
So, let's rescue this answer and see what a top band response actually looks like. It starts by defining the mass clearly as 5.0 kilograms. It correctly applies the gravitational field strength, little g, at 9.81 meters per second squared. The calculation becomes W equals 5.0 multiplied by 9.81, which results in exactly 49.05 newtons. Showing this exact level of clear annotation, heading structure, and flawless unit tracking is exactly how you guarantee you pick up every single available method mark.
Now, when we get into the higher-order questions that ask you to compare elastic and inelastic collisions, you have to nail both the similarities and the differences. A massive similarity you must state is that total momentum and total energy are conserved in both types of collisions, both of them. However, the critical difference, the one that actually scores you the evaluation points, is that kinetic energy is only conserved in a perfectly elastic collision. In an inelastic collision, some of that kinetic energy is transferred to other forms, like heat or sound.
To wrap up our core physical principles, let's look at this direct quote again. Always define your terms before using them in extended responses. Momentum is the product of an object's mass and its velocity. Weight is the product of an object's mass and the gravitational field strength. If you fail to clearly write out these parameters before jumping into some massive algebraic manipulation, the examiner has no way to verify that you actually understand the physics you're applying. Don't make them guess.
Section 6. Your next exam survival step. If you want to keep building this ultimate physics toolkit, you need to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE. This entire explainer series is heavily designed to help you excel in your Cambridge examinations. Mastering the structure of momentum and force calculations is an absolute essential foundation, and reviewing these core definitions with us regularly is exactly how you lock in those grade boundaries for good. But we aren't done yet. The mock survival plan and our deep dive into the examiner's matrix code continues in our next explainer. We're going to cover the absolute hardest command words found in Paper 2 and Paper 4. Knowing the physics formulas is just your baseline, but understanding the exact matrix of what the examiner requires when they ask you to describe, explain, or show that is what truly elevates your final score from average to elite.
So, before you go tackle your next exam, I want to leave you with this provocative thought. If momentum is always completely conserved in a closed system, where exactly does the momentum go when a bouncing ball finally comes to a complete stop on the floor? The answer to that relies entirely on how you evaluate command words and define closed systems. We are going to decode exactly how to answer that in the very next explainer. I'll see you there.